So today we're going to start looking at number patterns. Specifically, there are two different types of number patterns we're going to look at. One of them is what we call an explicit sequence. The other one is a recursive sequence. This information will be viewable in section 9.3 of your online textbooks. So the first type of sequence we're going to focus on is called an explicit sequence. And explicit sequences are nice because they generally give you a formula like n squared minus 1, and then you should be able to list in what is the first number in the pattern, the second number of the pattern, the third number of the pattern, and then you can even jump ahead and find something like the 50th or the 100th term in the pattern. Recursive sequences will not have that ability. You'll have to find all the numbers in between, but with an explicit sequence, you can jump ahead to whichever number in the sequence that you're interested in. So here are a couple examples. You can see that this one is adding 3 over and over and over and over again. So we could actually write a formula to represent that, and then we'd be able to jump into something like the 60th term without finding them all one at a time. This one appears to be multiplying by -2 over and over and over again. And then this one is actually, it looks like the second power of numbers. So 1 squared, 2 squared, 3 squared, 4 squared. So all of those are things you can do. You can do adding, multiplying, and exponents, and then create a pattern of numbers. So the explicit sequence is one where the nth term, by nth term I mean if I'm asking about the 50th number or the 80th number in the pattern, that's the nth term. It's going to be given as a function. So the first example, the kind of thing that you'll be doing in the homework, they will define the explicit sequence for you, and then they'll ask you to do something like find the first 6 terms, and then maybe find the 50th or the 100th. So the way we do that is we actually just replace the n with whichever number in the pattern we're interested in. So if I want to find the first number in the pattern, I would call that a sub 1. And then if you plug in 1 squared minus 1, when you evaluate this, you just get 0. So now I know that the first number in this pattern is 0. If I want to find the second term, then I'm going to plug in 2. So whichever number you're interested in, that's what you plug in for n. So the second term, now I have 2 squared, which is 4, minus 1 is 3. And I'm just going to keep repeating this process. So the third term is 3 squared minus 1. And then the fourth term is 4 squared minus 1. The fifth term is 5 squared minus 1, and the sixth term is 6 squared minus 1. So here's the nice thing about an explicit sequence. It's that they want us to go ahead and also find the 100th term of the pattern. I don't have to keep doing this one at a time. I don't have to find the 7th, 8th, 9th, and 10th to do this. I could just jump to finding the 100th term in the pattern by plugging in n is 100. And so the answer we'll get for that is 9, 9, 9, 9. So we have 9,999 for our 100th number. So if I was listing out this sequence the same way they had them listed up here at the top, I would just be saying 0, 3, 8, 15, 24, 35, and then 9,999. So now we're going to compare the explicit process with the recursive process. So a recursive sequence is one that defines this sequence of numbers by giving you the first term in the pattern and then telling you what you have to do to that first number to find the next number. The downside to a recursive sequence is it's not very useful for jumping ahead and finding something like the 10th term or the 11th term. You have to find all of the ones in between to get the answer. So it's more about the pattern that's given, basically. So for our first example, you're going to find the first 4 terms, and then we're going to jump to the 8th term of the recursively defined sequence, where the first term is defined, b sub 1 means the first number in the pattern, and then when they say b sub n, they're saying for any other number in the pattern, whether n is 3 or n is 50, it's -2 times b sub n minus 1. So pretend for a second that n is 5. This over here, if you plug in n as 5, you end up with b sub 4. So it's telling you that the fifth term of the pattern is based on the fourth term of the pattern being multiplied by -2. If you're trying to find the 10th term of the pattern, then you're plugging in n is 10. So the 10th term of the pattern would be equal to the 9th term of the pattern because of the 10 minus 1 multiplied by -2. So this is basically telling you that to find the next term in the pattern, you have to use the previous term and multiply it by -2. So this is defining the process or the pattern for going from one number in the sequence to the next. Take the number you know, multiply it by -2, that gives you the next one, and then just keep repeating that process. So they started off by giving us b sub 1. So b sub 1 equals 0.25. It was just given to us. B sub 2 is going to be equal to -2. And then, like I said, I'm plugging in n as 2, so that's going to be b sub 1 times -2. So b sub 1, we already know the answer to that. B sub 1 is equal to 0.25. So if you evaluate that, you get -0.5. Then we go on to find b sub 3. Well, that's going to be equal to -2 times, if I'm plugging in n as 3, 3 minus 1 is 2, so I'm looking for b sub 2 times -2. So basically, I'm just going to keep looking at the previous answer that I have. So now it's -2 times -0.5, which is going to equal +1. So b sub 4 will equal -2 times +1. And then here's the downside with recursive sequences. We found the first four terms. We know b sub 1, b sub 2, b sub 3, and b sub 4. But they asked us to jump to b sub 8. I can't just skip to b sub 8. This pattern is defined around knowing the previous number to find the next number. So I still have to go through and list b sub 5, b sub 6, b sub 7, and b sub 8. Well, b sub 5 is going to be the number I know multiplied by -2. That's the pattern here. The number you know multiplied by -2 to find the next one. So -2 times -2 is +4. And then the next number after that, if you multiply 4 by -2, that gives you -8. And then the next number is +16. And then the last one that we needed, the 8th term of the pattern, is going to equal -32. So again, just to describe what's happening here, when they define something as b sub n, they mean the term you're interested in. If you ever see a b sub n minus 1, it just means the previous number in the pattern. So when you're talking about b sub 4, you're looking at b sub 3 to get that answer. So now we're going to talk about whether a sequence is defined as converging or diverging. If it converges, then that means it approaches a specific number. It's kind of like there's an asymptote or a set number that's going to get closer and closer and closer to, but never actually hit. Now it will diverge if it doesn't approach a specific number, if it just kind of takes off and it's constantly changing and it doesn't seem to be approaching anything in particular. So the two cases we're going to focus on are when we have x to a power in the numerator and x to a power in the denominator, and then this is actually the same rules that we use for horizontal asymptotes. You compare those exponents on top and bottom for the x values. If the exponent on top is bigger than the exponent on the bottom, that's what this says, then you're just going to say that the sequence diverges. It continues up forever. It's not approaching a specific number. If those exponents are equal to each other, if the m and n powers are equal to each other, then you're going to use the coefficients of x. So if you had 3x squared over 2x squared, the exponents are both the second power, so you would just look at the coefficients out front, 3 over 2. And that would be the number that you appear to have a horizontal asymptote at, and that's what your sequence is going to get closer and closer and closer to. The numbers are going to get really close to 3/2, but never quite hit it. And then the last case is when the exponent on the top is smaller than the exponent on the bottom. So if the top is smaller than the bottom, then you will say that it converges to 0. So it's always approaching the horizontal line at a height of 0. The other case we'll look at is for when you just have a number being raised to a power. So there's no fraction on it. If you just have a number being raised to a power and the number is bigger than 1, even if it's something really close to 1, like 1.001, if that number is bigger than 1 at all and you're raising it to the nth power, then you will say that it diverges. if the number that you're raising to a power is somewhere between 0 and 1, but not including either of those endpoints, so numbers like 1/2, 1/4, 1/3, then that number is going to converge to 0. So let's look at a couple examples of this. So they'll ask you to determine if the sequence converges or diverges. If it converges, then you'll have to say what it converges to. That's what they mean when they say give the limit. Well, the first example, they gave us a couple of the numbers in the sequence, and then they actually defined that our pattern is n to the 4th power. Well, in this case, you can see that the numbers don't appear to be approaching a specific number. They just keep getting bigger and bigger and bigger forever. So it's kind of like we have a graph where the value is just taking off on the right-hand side. It's going to get bigger forever and never approach anything in particular. So in this case, we would just say that the sequence diverges. If diverges, no, you say diverges. Now, the next example, they define what the term is n to the 4th power. For example, they might be able to recognize this is 1 over power 3. So 3 to the 4th power, 3 to the 2nd power, 3rd power, 3 to the 4th power. These numbers are getting closer and closer to 0. So they're approaching the x-axis. So as this graph, as you get bigger and bigger in the sequence, it's getting closer and closer to the borderline of 0. So say it approaches to 0. That's the limit of 0 on this one. And in the last case, they define the same thing as terms for us. So we have terms that we plug in as 1, as 2, as 3, as 4, etc. But you notice that we have n in top and bottom. They raise to the 1st power more. So we compare that to the rule in the previous slide. We have the same exponent on top and bottom, which means it's this middle case. So converges, go take where the coefficients are. So what numbers being multiplied by the n's on top and bottom. For this example, I have 2 times n on top, 3 times n on bottom. So this one's going to converge to 2 over 3. So that's what you have to do. That's all for them. Thank you.